Today, we're going to explore the design and construction of Lea Lea Bridge, focusing on piling, splicing, and engineering solutions for remote and challenging environments. Good morning and welcome to our webinar on Lea Lea Bridge in Papua New Guinea. I'm Georgia Lance, Marketing Officer at Wagners CFT, and I'm here with today's guest speakers, Turra Holdings Project Manager, Tom Derby, and Wagners CFT Chief Technical Officer, Michael Kemp. Tom is a civil engineer who has been involved in various civil engineering disciplines on both contractor and client side, constructing roads, bridges, ports, airports, coal-fired and hydroelectric power facilities, remote hydrocarbon exploration sites in Papua New Guinea, and other construction projects across Australia and Papua New Guinea. Tom is currently working as a consultant for Turra Holdings Limited, the shareholders of which are the umbrella landowner companies for the upstream and downstream facilities of the Papa LNG project, operated by ExxonMobil. Tom has been involved in the Lea Lea Bridge design and construct project since contract award in March 2024 and worked closely with Wagners CFT during the design and procurement stage. He also directly involved with the successful construction of the bridge in April to June 2025. Michael is an ambitious CEO and business unit leader with more than 20 years' experience at Wagners, where he has spearheaded significant growth and innovation. Currently, he oversees Australian operations for Wagners Earth Friendly Concrete and is focused on expanding EFC into international markets. Michael is also responsible for the global growth of Wagners Composite Fibre Technologies and the technical development of new products. With a Bachelor of Civil Engineering from the University of Adelaide, Michael combines his tertiary qualifications with deep expertise in business processes, strategic development, and product innovation. We're also joined by Wagners CFT Marketing Manager, Kelly Stewart, who will be facilitating the Q&A session at the end of the webinar. Welcome, Tom, Michael, and Kelly. Before we get started, just a few webinar protocols. We are recording today's event and will make the recording public via the Wagners CFT YouTube channel. You can ask a question at any time during the webinar via the chat bubble at the top of the screen. However, we will hold your questions over to the end of the webinar for the Q&A session. And for anyone having difficulty accessing the chat facility, feel free to text your questions to me on the mobile number I have just popped in the chat now. So let's dive into today's webinar. I'll hand over to Michael and Tom.
Thanks, Georgia, and great to be with you all today. I'll just get my screen up and we'll get into the details today. How's that, Georgia?
Yeah.
Thank you. So today we're going to talk about basically a case study of a project in Papua New Guinea. As a bit of background, Wagners has been developing our fiberglass walkways for many years, probably a 20-year period, where we started with very short footbridges in Brisbane, and we've now extended that to some fairly significant structures around the world. Just an example of some of those, I guess, in the lead up to this project that we've used as precursors. So, this one's at Southwest Rocks in New South Wales, replacing a timber structure with a fully fiberglass structure. The timber structure has since been taken down, where we used bonded members as girders and handrail posts, but on existing steel piles. And again, many other similar smaller structures around Australia with our handrail systems and substructure systems, and through to some fairly significant structures. So this is the Elizabeth Bay Marina in Sydney, where from an aerial view, you can't see any of our composite product, but underneath all of that timber decking are fiberglass beams holding up the whole platform. So with a lot of experience in, I guess, taking composite materials, which are the right material for the environment, corrosion-free, lightweight, and generally easy to install over salt water, we'll now progress to Townsville, probably our most recently installed over water boardwalk. And this one, I just wanted to point out to everyone's got a really great webinar done by the installation crew with some great time-lapse footage of it being installed as well. So that's available on our website. So through to the current project, I'll hand over to Tom to give us some background on the structure. And then we'll come back to me for some design work, and then back to Tom for the installation that he coordinated. Tom, I'll hand over to you.
Okay, thanks, Michael. Yeah, so the original Lea Lea footbridge was constructed 2012 under an ExxonMobil tax credit project. And while they did a really good job of the decking, the support structure wasn't the best, and they had poles that were fairly inferior quality. The structure is across his Lea Lea inlet, which is around 40 kilometres west of Port Moresby in Central Province. So you'll see we have Lea Lea and we have Lea Lea. So apparently there was an expat came to the area many years ago and misheard the name of the village, and it's been called Lea Lea ever since, but it's actually called Lea Lea. So there's a bit of a campaign to get it back to the original name. So that's why there's a bit of a mix and match on names there. So we have Lea Lea 1 and Lea Lea 2 villages, total population about 8,000, approximately 3,000 are on the far side, the western side of the bridge site. Total length of the crossings, 220 metres. So the existing structure collapsed in October 2023. The locals had to rely then on ferrying across the river. However, they did an excellent job. They built a temporary structure just with local labour. They got mangrove poles, used the existing deck structure, and in about 5 or 6 weeks they built a temporary structure, which allowed the locals again to cross over the bridge site. A bit fortuitous for us, this bridge structure collapsed about 2 days before we actually started construction, and that made construction for us quite a bit easier. Unfortunately, the locals had to go back to the ferrying method again. We did speak to the locals about what sort of structure they wanted as a replacement. They insisted they didn't want any vehicles, any vehicular traffic in their village, and they wanted to stick with the footbridge structure. So, and going with that, we decided on a 2-metre wide deck, which is pretty similar to what was there originally. If we can maybe go on to the next slide. So the Department of Works contacted Turra to put together pricing for a design and construct solution for the replacement bridge. And the project, again, being funded under ExxonMobil tax credit program. We had a gentleman who's been in Papua New Guinea a long time, and he's a consultant to Department of Works, and he suggested he'd heard of the Wagners product, and he suggested we contact Wagners and get something underway. So Turra contacted Michael, and proposal and pricing were put together. The Papua New Guinea at the moment, for the last probably 10 years, has had a real problem in foreign exchange. To get foreign exchange to buy products from outside Papua New Guinea, there can be a waiting time of anything, depending on the size of the order, anything up to 6 months. So because of that, we went to look at an internal supplier who provide timber decking. So we've got a proposal put together, pricing, which involved steel piles, steel superstructure still, which again had to be imported, but the timber decking would have been locally manufactured. We took that to the client's, the Department of Works steering committee, and they agreed that the Wagner CFT solution is much superior, mainly due to minimal maintenance requirements. Maintenance is a huge problem in Papua New Guinea. There's 800 languages in Papua New Guinea, and none of them have a word for maintenance. So the fact that it's in a marine environment made that even more important. So we can have the next slide, thanks. Okay, so I think this is on the detailed design, and I'll hand back to Michael.
Thanks, Tom. So after we got through, I guess, a tender process and Wagners were commissioned, we got straight into the detailed design phase. The first thing that we were looking at, even probably before commissioning, was just what type of structure is going to best suit the local location. So I think really that from almost, our first contact, we were considering, okay, what type of structure, what spans are we looking at particularly? So we were able to put together, I guess, ballpark cost estimates based on different configurations. So here you can see that Southwest Rocks project that I had up earlier was roughly 7-meter spans between bents, or between the pile groups. And you can see in the top right corner of the schematic where we've got roughly a 375 deep girder and effectively an 1800 trafficable width on that walkway. So we were able to sort of put together an order of magnitude cost estimate based on a series of those spans for the length of the structure. And then the same, but based here on a 24-meter span. So typically we're operating from 6 meters to 30-meter span configurations at CFT regularly, and we're looking to push that envelope on larger span structures. But I guess that the bulk of our work today is in that range. So we were able to put together, based on a 24-meter truss that we'd effectively just made and installed, we have some pretty good accurate costing on it. So we could compare the cost differential between, I guess, 7-meter spans and 24-meter spans. And whilst when you go to the larger spans, you're getting a higher cost per square meter in your superstructure, but you're getting a lower cost in your piling because you're putting in a smaller number of piles. Each pile group will need to carry more load. So it's always this trade-off, this balancing act between the size of the piles, the span of the superstructure, and at the end of the day, making sure we get the right result. One other key component in this was the mass of a superstructure. So from, I guess, the early stages, we were really looking to design a solution for installation. So we were talking to Tom and his team about what sort of size or what sort of mass could they lift. So, a 24-meter span truss that you see there needs a much bigger crane than the 7-meter span above it. Slide. The design criteria, Tom mentioned that we weren't looking at vehicular loads. Where we ended up was, I guess, using what we knew about Australian codes. This was our first job in Papua New Guinea. So I guess some of the changes we had to look at the local, you can see there, Papua New Guinea specification 1001. We had to look at the local requirements. We ended up engaging Kramers, an engineering firm that has offices here in Brisbane, but also very local in Port Moresby, from that basis. So good familiarity with both to take, I guess, what Wagners knows well, which is certainly Queensland and Australian design criteria, and correlating that with the local requirements in PNG. So, but at the end of the day, very similar to what we would do on most of our structures. So a 5 kPa pedestrian load, now it's pattern loading, so it could be 5 kPa on any sort of individual spot. And then a 1.4 kilonewton point load. The wind conditions were from the Papua New Guinea spec. We also had to consider earthquake in PNG, which is not something that's, I guess, readily is considered on occasion in Australia, regularly in New Zealand. But yeah, not so much in the Australian condition. We ended up, from a cross-section point of view, we went with a 10-metre span. I guess the difference between our earlier versions there was that we'd recently come up with this 250 by 100 pultruded profile. So you can see it here. Hopefully you can all see my mouse. And we're bonding 2 of those together to make a 500 deep bonded girder. And we could use 4 of these to meet the requirements, 4 of those girders across the width of the walkway. So we're able to achieve that 2 meters inside handrails that Tom mentioned earlier with those 4 girders. We like this, the cross section, fairly simple methodology, 4 girders, some diaphragms, and handrail posts bolted directly onto the outside of the exterior girders. Fairly simple in design, not dissimilar to, you know, a timber structure from years gone by. And I guess really considering what had happened previously with the other structures being taken out, I guess, by, you know, quite a significant tidal flow every day, significant tidal range. So we elevated the deck level, you can see here in the yellow, to 3.8 metres. So it's quite a bit higher than, I guess, where it was, with HAT at 2.3. So what that does is it gets I guess, the bulk of our superstructure, so pretty much everything you see in the picture there, above that HAT level. So our superstructure is not in the tidal flow acting and having that big force applied to it. So yeah, the area in the tidal flow is limited to the piles and the bracing of the piles, and the deck is not catching a whole lot of force that we need to transmit through the piles to the ground. So a bit more detail here. So that again, you can see the 500 girders, diaphragms. So we use diaphragms in bridges generally to help our handrail loads. So when we get a horizontal load applied to the top handrail, we have to limit the deflection of that handrail by the codes. And if you just have that post attached to one girder only, it does allow a rotation, and a small rotation in the girder creates a large deflection at the top of the handrail post. So we try to effectively brace that external girder with a diaphragm. So we're connecting 2 girders together, and that restricts the rotation of that outside girder, and therefore really helps with the deflection at the top handrail post. So typically you'll see on our structures that diaphragms are at or very close to handrail post locations, and that's why. We also determined, and this was more of a functionality point of view from an installation, that we didn't need diaphragms to go across the full structure. Sometimes we'll put them across the whole structure to, I guess, connect across the full width. But from a practicality point of view and in discussions with Tom, we wanted to sort of prefabricate the main beams here in two halves. So we've got basically taking them with the diaphragms pre-assembled. It also matched the amount that could be lifted with the cranes. So we really tried to think about how it was installed as we're designing the project. You can see here the 10-metre spans. We've got 2 metres between posts, and you can see the diaphragms at or very close to those post locations. They'd be offset in this case just for ease of getting to bolts for assembly. That's probably the most important things. The piles. So following that geotech report, we had a few issues in interpretation with the geotech report, but we knew the forces that we had to withstand. And the 300 diameter profile has been used as piles, and we've allowed for some bracing here. Now, with the bracing, it was designed for bracing only above lowest astronomical tide. So we didn't, and it was a fairly important thing for Tom, we didn't want to be trying to install any bracing underwater. We just didn't think that, A, there wouldn't be the capacity to do it, B, difficult and expensive. So we've designed that structure to have bracing above LAT, so that, at worst case condition, you're at lowest astronomical tide assembling a bolt before the water starts to rise. Just another thing that we are generally very keen on is this design verification. So all of our material properties that you see in Wagners design guides and product guides are all derived from testing. We do attempt to do it from theory, but anything that's published will be or used in a design exercise will be verified with testing. So here, for the 500 girder, I mentioned it was a newer profile. This is one of the first projects to use that 500 deep girder. Now, we've done many projects before with bonded pultruded assemblies, so it probably wasn't a big stretch, but it's still worth verifying. So this is a typical 4-point bending test. So we're applying the load at 2 points, where you get a constant moment region in the middle, and very typically, I guess, we didn't get a tension failure or a flexural failure. Our failure mode ends up being a local compression buckling underneath one of the load application points. So bear in mind that for a pedestrian bridge only, no vehicular load, that the failure load of one of our girders, we've got 4, the failure load of one of the girders was about 14 tonne as a point load. So they're significantly strong. Typically with composites, we're designing for deflection, and many of our webinars, we talk about E40 being a critical design criteria. So that's the Young's modulus of our materials. For deflection, we're using 40 GPa as the modulus. So it's the key material characteristic, I guess. And it's probably one of the real differentiators. In Europe, there are 2 main levels that they talk about in the European standards for composites. They talk about a modulus of 17 or a modulus of 23 GPa. They were set up to separate European manufacturers from Chinese manufacturers originally. Today, Wagners designs with a modulus of 40. So E40 is where I guess you should be looking for your next project. This test came up with a modulus of 46 or close to 47 GPa. So, and we would expect that. So anything that we test, we downrate our capacity for structural variation. Now, this is the same as steel. It's the same as any other construction material that's used against known standards. So we're not being ultra conservative. It's more of it's a risk thing. It's making sure that your product does what the standard says it will do. So if you take any of Wagner's products and test them, they should achieve a higher number than what's in the design guide. Going on to design for installation. So we always had the capacity to splice our piles. One of the key issues with piling is that you never quite know what you're going to hit. The geotech report was taken slightly upstream from the exact location that we were working off. So we initially had quite a few questions between Tom and myself, on how we're going to handle the piling. There was reports of a deep layer of silt, which initially we thought we wouldn't be able to get any capacity out of. When we got to site, that silt layer was not there. So that was probably upstream where the test was taken, but not where we were. So we did design the piles with splicing in mind. And I mentioned earlier how with the superstructure, we were looking to manufacture it in the two halves. So you can see here, we sent up an installation procedure manual to Tom to review before getting onto site. And we've got, the red square and the blue square that they're intended to be made as two halves. And you can see on the left a photo of Tom's crew pre-assembling two girders with diaphragms in a yard before they were put onto a barge and then carried around to the site for installation. So all of these things, need to be considered at design time. That the mass of each lift is generally a key thing, particularly over water, or on a more remote site where you're governed by the available crane. If you're in the middle of Brisbane or Sydney, you might be able to call in a big crane for a big lift just because of availability. But often if you're outside of these centres, you've got the crane you've got, and we try to work with that and design a process that allows those cranes to be used. I'll hand back to Tom to discuss installation.
All right, thanks, Michael. So installation, as we say, based on the geotech report, and it was Michael that recommended that we should go down with an undersized drill, and we finished up buying an auger, a 250 diameter auger that could go down maximum 9 meters. And then Michael recommended driving the piles with either a vibro hammer or impact hammer. So we looked at various options and what equipment we had available. We had a Kobelco excavator that our subcontractor RMC had, and we based everything around being able to use that with the vibro hammer, the impact hammer, the auger, and also the capacity to lift the girder sections onto the completed headstocks. So we finished up purchasing a side grip vibratory hammer, which turned out to be extremely useful to pick up the piles, maneuver them, put them in position, drive them down to their as far as they could go with the vibro hammer. That worked out really well. It was a saver for us. To finish off the piles, we got a relatively small rock breaker, designed a plate, 50mm steel plate that we put on the end of it, and we used that as an impact hammer to finish the piles down to design depth or refusal. The FRP material, the pile's 12 meter long. So Michael came up for a site visit one day and he looked at me and he saw these guys, 12 of the guys had the slings around the pile, and he says, for goodness sake, these guys aren't going to pick that up, are they? And they picked it up, no problem, moved it around, set it in front of the excavator, allowed the excavator to pick it up. So it's very easy to work with. And again, with the lightweight nature of I think the beams together were about 400 kgs each beam, so it was quite easy to lift them into place with the excavator. Next slide there. So we drove the first two piles on the abutment, and we confirmed with Wagner and Kramer what sort of load capacity was required, and we came up with 15 ton per pile. So we got together some crane weights and put them on gradually. let one on for an hour, next one on for another hour, and built them up to the 15-ton capacity, left them for 24 hours. Bad connection here at the moment. But the result was excellent. With the pile moved 1 millimeter with the 15 tons on it. 24 hours later, it was taken off and it recovered that 1 millimeter, so basically zero settlement. We installed the first 5 bents from the beach, just using a frame on the ground, and that allowed us to figure out what was the way to the installation procedure with the auger, and really the augering was the critical thing. If you get the hole in the right place, then the pile will follow, and we found that all the way through. One of the biggest issues was if we tried to do augering when the tide was really moving in or out, it was a problem. So we had to wait for the before we could do the augering. But if we got the auger location correct, then driving the piles was no problem. And next slide there, Michael. Yeah, so after the first 5 bents, we had a decent sized barge, 50 by 12 meters, and we moored that. I think we had to do 8 shifts. We could drive 2 bents from each barge location. Our subcontractor came up with quite an ingenious method to set up the. You had swiveling arms on each side, 10 meters apart, and that allowed you, even if your barge location was slightly out, you had a fair bit, 2 meters probably. You could adjust the swiveling arms to set up the correct location for the piling.
Tom, could I just ask
have
a
a bit of
question on
trouble.
that? Is that the swiveling arm here? I'm pointing. Hopefully, you can see my mouse. Is that the swiveling arm there that you're referring to?
Yeah, it goes right back. You see, it's got a large, I think it's 200 diameter pin weight there. Yeah, so each one is pinned there and goes out, and you can just move them back and forward to suit. And then that small piling frame is just set up with pile locations, and we were initially using a Topcon GPS unit to do the location, and that just became a bit difficult for various reasons. And we found out the best way was just to sight it through, measure from the previous bent. The good thing about this bridge, it didn't matter if it landed 1 meter or 2 meters too far or 1 meter less than the actual design location. It landed where it landed, so that made things a bit easier. So as long as you get the alignment reasonable, measure 10 meters, bang, piles in. So it worked well.
But Tom, we did allow for a bit of play, I remember. So in the beam length,
yeah.
I think we supplied the beams over length,
which
right, allowed you to drive the piles and then measure and then cut the beams to suit, I think.
And cut the beams, yeah. So the beams were 10-meter span. I think the beams were 10.2 meters. And the whole thing worked out very well. You have quite a bit of leeway with the piles in this system. You've got, as we say, 200 millimeters either way, probably longitudinally, and transversely probably 150 mil at most. But,
and Tom, could you just talk about the depth of the piles? You were driving through how much water and how far in?
Yeah, so the river, the inlet runs, it's shallow on the eastern side and gradually gets deeper to about 3/4 of the way across, and then it's the bed level at the deepest points -3.6, and then it rises fairly steeply to the western side. So we were driving the piles. We just needed to get a decision on what the minimum depth was. There was a few queries about HAT, but we finished up with minimum penetration of 4.5 meters. Initially, we drove some of them down to 8 meters depth, and the one we had to splice one bent where we went a bit too far with the pre-drilling. Yeah, so there's the splicing there. And unfortunately, we didn't have any splices there, so we had to leave the decking out over this. I think it was between bent 4 and 5 and 5 and 6. We had to leave those out for a few weeks until we got the splices up, and we just kept on going with the piling. But the splices were very simple to put in, external splices with, you can see the bolts, 4 bolts top, 4 bolts bottom, and the opposite axes, and that went very easily, no problem. So once the 2 bents were driven off the barge, the piles were cut off to the final level. They drilled for the headstocks, and then we didn't have a piling frame, wasn't, and future we'd probably get one that you could bolt it apart and pull it apart and lift it off, but this one you had to slide it up over the piles to get it off. So we had the holes drilled, headstocks ready, slipped the pile frame off, just put a temporary platform on the swiveling arms, and installed the headstocks, then lifted the beams on, and did that all progressively. So the barge would sit there, get the headstocks in, put the beams on, all ready to go, and then move round to the next position. So so as Michael has said already, that's a pre-assembled double beam section with the handrail posts installed. That was dropped onto the headstocks. Second one dropped in, bolted up, and then the handrails, the decking installed progressively behind the beam installation.
Tom, how did you find you made those sections off site? Maybe just give us a quick. You had a yard sort of around the bay. Yeah,
that's right. So we had a yard about 20 kilometers from the bridge site. We pre-assembled them. So we had, I think it's maybe in the next slide, but we had Wagners technician came. He spent overall 3 weeks, couple of visits. He spent 3 weeks there and explained to the guys how to do all the pre-assembly and then obviously the installation of the headstocks and the bridge superstructure on site. So we assembled them off site, put them on a 6-meter truck with a long overhang and drove them up the road to the bridge site. But it really worked out very well. And very simple to go together. Once the guys had been schooled on putting all the beams together and the decking and the whole superstructure, once we'd got the methodology over to the boys, they just worked themselves and no problem at all. They did a great job. If you go and look at the deck, it's incredibly straight. It looks really good. As I say to everybody, it's the best looking bridge in Papua New Guinea, I reckon.
Very good. And Tom, I just noticed there is a question in the chat, but it might be the right time to answer it. Could you talk about like production rate, like how many piles a day did you drive, or how many spans a day did you install, or a week?
Yeah,
or like
so
how did you think of that?
It took us obviously there was the first 5 bents and you could easily do a couple of piles a day. Our goal was to drive 4 piles a day and then spend the day that this was off the barge, drive the 2 bents in one day and then spend the next day installing the beams, which we managed on one occasion, but for various reasons, the construction issues you have along the way, we didn't manage it all. A lot of the problems were survey initially, trying to use the TopCon system. We had major delays with getting the piles set out and organising that. Once we decided just to align the things by the string line and dumpy level, then that really improved. Got rid of all the survey delays. But yeah, I mean, if once we get into the scheme of things, you could drive 4 piles a day auger and dry 4 piles a day on a good day, and drop in the beams the next day, bolt them up, and relocate.
So looking at this picture, Tom, it's sort of, you're getting a span a day. Is that what you're saying? You drop in 4 piles and drop the superstructure?
Yeah, you can do on a good day. And once, you know, if we ever did this again, we could manage that. Obviously you learn a lot of lessons. It's the first bridge of its kind in PNG, and the methodology we used was the first, I guess, has been used in a bit of a pioneering methodology that hadn't been used in PNG before either. So it's definitely a bit of a learning curve there, but if we did it again, that's what you would work on, 1 span a day. Yeah.
And just a finished shot, I guess, to conclude our presentation today. Tom, we've got I'm coming up or starting to head your way tomorrow. What can you tell us about the opening and what it might mean to the community?
Yeah, it's bigger than Ben-Hur, Michael. It's quite a lot of dignitaries will be there. There'll be a lot of speeches. If you arrive an hour late, I don't think it'll make any difference. So they've got dancing groups, singing groups, and then speeches for a couple of hours. But it's a huge thing for the community, and they were incredibly supportive. You work in various locations in Papua New Guinea, and it's a nightmare. You just get held up every second day. Or one of the jobs we're doing up in Hides at the moment, it's every day you get shut down because of. So it was the community were incredibly supportive. Obviously, it's a great advantage for them having a bridge that will last them for 50 years plus. But yeah, no, they were incredibly supportive. We employed quite a number of additional people than we probably would have done in a normal project. We used a local women's group to supply lunches for all the workforce. So I think that's Turra's philosophy. We try and do as much as we can, whichever location we're working in, try and provide as much opportunity for the local people as we possibly can, and try and leave a bit of a legacy. And we had a lot of tradesmen from around the place who learned a lot on the project, and we just need to try and find some more locations to put these bridges in, Michael.
Very good. All right, Georgia, we'll hand back to you at that point. And yeah, so we can move on to some questions.
Okay, so thank you very much, Michael and Tom, for your presentation. Just before we dive into the Q&A session, I want to quickly tell you about Wagners CFT's new cutting-edge filament winding technology and Trident marine piles. Let me share my screen. Okay. Wagners CFT is excited to share a major step forward in our manufacturing capabilities, the introduction of filament winding technology to our production line. This new process opens the door to a much broader range of products. We'll now be able to create larger, tapered, and custom-shaped FRP components, something previously not possible with pultrusion. Filament winding also brings flexibility to our production. By adjusting fibre angles and placement, we can optimize each part's strength and performance. It's a much more efficient, perfect for delivering high quality, tailored solutions to meet the unique needs of our customers. So if you'd like some more information on filament winding, use the QR code on the screen or reach out via the website. We'll also include the link to this information in today's follow-up email. Wagners FRP Trident marine piles are manufactured in Australia from fibre reinforced polymer and coated with a high density polyethylene outer sleeve. They are designed to perform for 50 years and reduce impact to berthing vessels. The dynamic properties of the Trident marine pile allows it to yield before returning to its original state, which significantly reduces the risk of impact damage. Twice as strong as steel, Trident marine piles are also inert and will not rot, rust, or corrode. And with no electrolysis, boat and marine hardware is safe from damage. So if you'd like more information on Wagners FRP Trident marine piles, use the QR code on the screen now, and we will also include it in the follow-up email. I'd now like to welcome Wagners CFT Marketing Manager, Kelly Stewart, who will be facilitating the Q&A session of the webinar today. Let's have a look at some of those questions, Kelly.
Thanks, Georgia. We might actually start very quickly just by asking Tom Derby to give us some more details about Turra. We didn't really go into depth about Turra as a company or a business. If you could just tell us a bit more about it.
Yeah, thanks, Kelly. Turra is it's a joint venture between two landowner companies. One who is the main umbrella landowner company in the upstream part of the Papua LNG project, and the other one is in the downstream side of the LNG project. So it's Hyde's Gas Development Company and Laba Holdings. So it put together, a lot of it at the instigation of ExxonMobil. Traditionally, landowner companies and PNG on the major projects, with the larger companies have stuck to security, plant hire, labour hire, and low complexity work. And Exxon's idea is to try and get a landowner company that is the capability of eventually taking on EPC work and taking on work higher complexity. So we've only been in existence since November 2022, but we've grown fairly exponentially since then, and a lot of our work is with ExxonMobil on the Hyde's gas conditioning plant and the infrastructure work outside that plant, and we do a lot of the infrastructure tax credit work down around the LNG plant and around Lea Lea and to the west of Port Moresby. Bridges, obviously, and road maintenance, and we have a water project, design and construct water project that we're working on at the moment. So it's quite an exciting time that we've grown exponentially over the last couple of years, and looking at a really good future.
So the majority of the contractors or people who worked on the project were local people, and this would have been their first time constructing with FRP as well. How did they find the material? How did they find, the differences and the nuances of FRP?
Yeah, no problem at all. We had some good tradesmen working on the project who they've experienced from the foundation project with the LNG, and so they're good tradesmen, experienced tradesmen. So they picked it up very well. Obviously, too, the Wagners supervisor came down and spent some time with them, and he was very impressed with the skills and how quickly they picked it up. But it's very simple, how to put the structures together. It worked really well. Yeah.
Yeah, but I did notice throughout your presentation, you did appear to work really closely with Wagners throughout the delivery of the project, and tap into some of those services and resources that Wagners offers with regards to having, expert knowledge on site to kick off a project. How important is that on a project like this?
Yeah, no, absolutely. Very important. And Michael was very good. He's obviously had a lot of experience, and he made a lot of good suggestions early on in the piece with regards to piling and the construction in general. So, and the methodology, we had a couple of sessions there with Michael and our subcontractor, and that really put the whole thing in place and helped us with how we put together the methodology, for sure. So it was good.
Let's jump into this question from Jeff Armstrong. He was just wanting to know debris impact, what was considered for HAT flows.
Yeah, we always have to consider impact. So typically we're looking at main roads in Queensland talks about logs floating downstream. So that's always the worry. I think keeping the bulk of the superstructure sort of a metre above HAT limits the debris mat that we have to worry about. So we did allow for it, but it's not encompassing the full height of the handrail. So, if we were at if the deck level was at HAT, for example, we'd have to assume that whole handrail system was collecting debris coming downstream. I think you can see, hopefully that last slide that we showed, you can see that there's a fair bit of waterway area underneath the structure for most of the time. So the impact at HAT is going to be minimised. And because of that tidal range, it's not like it's going to stay on there either. It will drop away as the tide flows out. So yes, we allowed for it. We always have to allow for impact, and it's very much a case-by-case or a location-by-location decision.
Yeah.
Do you want to?
Sorry, Kelly.
Sorry, Tom.
I guess we should just say this isn't a major river system. It's really an inlet. So the debris coming down through there is relatively limited. The biggest issue is that the speed of the tidal flow. When it comes out there, it does go quite quickly on the outgoing tide. But once it gets down to sort of half tide, it's moving fairly quickly. But debris-wise, it's not so much of an issue.
What was LAT, Tom? What was that tidal range?
So it goes 0 to 2.3. If you look on the left-hand side of the bridge there, there's a cul-de-sac, a bitumen cul-de-sac, which the locals tell us has never been submerged, and that's at 2.0.
So, but every day you were seeing at least 1.5 meters of tidal movement, right?
Yeah, that's right. Yeah. So it's about 2.3 max.
And the velocity that it flowed out was substantial. I was probably surprised on my first trip just that, you can see around the piles, you get a bit of an eddy at the backside of the pile where the water's flowing out. So it was a significant flow to, hence the 4.5 meter embedment that we required on those piles.
Yeah,
it was mainly we're trying to resist the flood forces, not flood forces in this case, but tidal forces, more so than the vertical loading.
Yeah, that's right. Yeah, and we did discuss it before, but the previous temporary bridge that was in there, the poles, there wouldn't be a pole that had over meter embedment, and that the reason it fell over was because they rotted away halfway up the pole. So I think 4.5 meters. I don't think we'll have a problem.
Can we just touch base again on the expected service life of the bridge now it's completed too, Michael?
Yeah, I think I haven't got the drawing set in front of me, but I think we designed it for 50 years. But we've got systems like this with up to that 80, 100-year design life around them. So the point is manufacturing elements that won't corrode, using elements that are inherently corrosion free in this environment. That's the key thing. We see a lot of steel structures in these locations, whether it's in salt water, whether it's in a mining application where there's a lot of corrosive materials. And I guess our approach has been we're starting with the wrong material. Let's start with a material that inherently resists corrosion and then build a structural solution around it.
We might touch on this last question that's just come in as well from HM Engineering. They're wanting to know about the recommended method for removing algae or moss from bridge piles submerged in water. This will be a good one for you to answer, Michael.
It'd be a good one for the whole industry to answer, I think. Generally, the key thing, I've seen, piling in. As much as Tom said I was helpful at the start, I've learned a lot from Tom, and I've learned a lot from this project. And I think every project we go to, we learn a lot from. So I definitely do not profess to be an expert. What I've seen is that if you have, for example, a concrete pile, concrete's generally fairly porous, that promotes or allows algae and so on to attach. If you allow attachment, it will grow and grow readily. The FRP pile is it's a fairly solid element. There's effectively no porosity or very little porosity, so it is hard to attach in the first place. We haven't got any there are paint systems that have effectively, what's the right word? Effectively poisons in them for algae to prevent algal growth. We haven't done that. And if you look at ships in ocean-going vessels, basically they're trying to use a very smooth finished paint to resist algal growth. So I guess that's the approach we've got, is that we've got a very non-porous pile. I am yet to see anything that algae doesn't grow on eventually.
Yeah.
So as far as
within a few days, Michael, there was algal growth in these piles.
yeah.
So you're never going to stop it. But I guess this probably the speed of the tidal flow is going to try and probably limit the amount of growth that's possible there.
Yeah.
We might jump to Sibin's question. He is dialing in from Nepal. Hello, Nepal. And he's wanting to know, can systems like this be used in high-velocity river systems like they have in Nepal?
It's just a matter of designing for the conditions. So I can speak of, to use a local to Brisbane example, in the Gap in Brisbane, we've got quite a hilly terrain, a lot of fast-flowing water in a narrow channel, so it can be, we end up designing for a flood velocity, and in this case, it's always cheaper to try to keep your superstructure out of that flood flow, but if you're in it, you've got to design for it, and you have vertical loads from whether they're trucks or vehicles or pedestrians, and you've got horizontal loads from your water force or debris mats. Or in North America, ice flow we've had to design for. We've actually had a couple of occasions on road bridges in the US where the horizontal force from ice building upstream was greater than the traffic load. So it's simply a matter of understanding that local condition and designing for it.
I'm just going to pop a link into the chat there at the moment as well. If anybody does have a project that they want to do a deep dive with Wagners CFT, you can complete that form that I've just put into the chat there. You can get together with some of our knowledge experts like Michael Kemp and talk through the specifics of a project and seek solutions through that deep dive process. So that is there, Sibin, if you'd just like to think about that for any projects you've got coming up. We might call this the last question as well. Sam is wanting to know, have we got any high-level comparison on materials that were used for the project compared to what they would have been if we'd used more traditional materials?
Look, I probably don't off the top of my head, Kelly, but I think what I'd say is that if we use steel, for example, on a structure like this, and Tom, I might give you the floor in a second as well, but you'd see corrosion quite rapidly. You'd be very reliant on your coating system, whether it's galvanizing or painting or whatever you used, and also the lifting methodology, the installation methodology would have had to be quite a bit different. You'd be looking at probably the piles would have been 2 ton instead of 400 kilos. A 10-meter span would have weighed probably 3 or 4 times as much per lift. So I think it would have. So I haven't got a direct tonnage comparison to give you today, but I think it certainly would have impacted both installation and whole of life. Tom?
Yeah, no, for sure. We're just pricing another project, 12-meter 250 UCs. 73 and they're 900 kgs per pile. We wouldn't have been able to use a 26-ton excavator to install them, that's for sure. So we'd have needed, a 50-ton crane sort of minimum. But really, the whole thing is about maintenance. We put cathodic protection in, but Papua New Guineans, they just don't have maintenance in their psyche, no matter what you put in place. So it all came down to that really at the end of the day for the selection of the CFT. Just and especially in this environment, wet, dry, the coatings, and they're going to get boats tied up to the piles, so it's be a continual problem. Doesn't matter what coating system you put on. It's a real problem.
Great. That's 11 o'clock, so I might hand back to Georgia to wrap it up. Scott Weatherall, I see your question there. We'll circle back to you after the webinar and answer that one for you. Georgia, I'll hand back to you.
Beautiful. Michael, if I'll just get you to stop sharing your screen and I'll get mine up for everyone. Okay. That concludes our presentation for today. A big thank you to Michael and Tom for their involvement, and thank you to Kelly for facilitating the Q&A session. If you'd like to share your thoughts on today's webinar, please feel free to complete the feedback form by using the QR code on the screen or the URL that I will just pop in the chat now. Or perhaps you'd like to be a guest speaker. If that's the case, fill out the feedback form and let me know, or reach out to me on LinkedIn, send me an email or give me a call. However you want to contact me, I would love to hear from you. Coming up in August, we'll be exploring the newly launched Signature Series, Pre-Engineered Pedestrian Bridge Solutions. Our best designs from the last 25 years, boxed in kit form and ready to provide quick, budget-friendly solutions for your next project. With guest speakers, Wagners CFT Project Delivery Lead Mitch Kelly and Lead Estimator Scott Brown. So if you're interested in this webinar, just use the QR code on the screen now to register for your free online seat or to receive a recorded copy of the webinar. The link is also in the chat now, and we will include it in today's follow-up email. That concludes our webinar for today. Thank you very much for coming, and we're going to go out on the video of the Lea Lea Bridge construction from the beginning of the webinar. Enjoy, and we look forward to seeing you next time.